In this video tutorial, we're going to be talking about quantum state tomography of photoelectron wave packets. My name is David Busto and I'm an assistant professor at Lund University. In an earlier video, we discussed about the fact that when we ionize an atom with a short pulse containing many frequencies, we create a superposition of many continuum states. And in the case where we fully transfer the coherence properties of the light pulse to the electron, we can then describe the photoelectron as a photoelectron wave packet characterized by spectral amplitude A and a spectral phase delta. However, in many situations, the ionization process can lead to the formation of multiple electron wave packets associated to different ionic states. In this case, if we do not resolve the final ionic state, these different wave packets overlap incoherently, and it is no longer possible to describe the electron using the wave function formalism. In this case, we need to move on to the density matrix formalism. We will now describe a quantum state tomography protocol that allows measuring the quantum state or the photoelectron density matrix. Again, let's start with the ionization by the short pulse. We create a broad superposition of continuum states indicated here with the shadowed purple area. If we take a spectrometer and measure the photoelectron spectrum, this will give directly access to the main diagonal of the density matrix, which is known as the populations, which gives information about the probability to find the electron in a given continuum state. The key challenge is to measure the off-diagonal elements, which are known as coherences. To do so, we need to do an interferometric measurement. And in this case, we use two infrared components with frequency omega-1 and omega-2 separated by delta omega that induce interference between two intermediate continuum states, epsilon and 1 and epsilon 2, to a given final state epsilon f. When we change the delay between the XUV and the infrared pulse, this will lead to oscillations in the photoelectron yield in the final state, such that the amplitude of the oscillations is proportional to the modulus of the coherence element between epsilon 1 and epsilon 2, while the phase is equal to the phase of the coherence of that density matrix element. So using this measurement, we now have access to one point in the off-diagonal elements. In reality, we can measure the amplitude and phase as a function of the final kinetic energy, which then gives us access to a full off-diagonal element, full subdiagonal. Using the fact that the density matrix is Hermitian, then we can get access for free to the other symmetric subdiagonal. If we want to get access to more subdiagonals, what we can do is that we can change the frequency separation, delta omega, between the two spectral components and repeat the measurements, obtaining in this way multiple density matrix subdiagonals until we reconstruct the full density matrix. This technique is called Kraken, which is a Swedish acronym that stands for Quantum State Tomography of Attosecond Electron Wave Packets. So let's move on to the experimental measurements. Here on the left, you can see the infrared spectra that were used for the measurements, and on the right, you see the corresponding photoelectron spectra. At the top, you can see that we use a single spectral component for the infrared, and when we scan the delay between the XUV and the infrared, we simply observe a cross-correlation trace with no oscillations at all. As soon as we superimpose a second infrared spectral component, we start seeing oscillations in the photoelectron yield. The oscillations are faster and faster as we increase the frequency separation delta omega. We can then analyze each of the spectrograms by taking the Fourier transform and looking at the amplitude at the frequency corresponding to delta omega. These are the amplitudes that are shown here, where we can see that the amplitude goes down as we increase delta omega. These amplitudes can then be directly inserted in an initially empty density matrix. the one corresponding to delta omega equals 0 corresponds directly to the populations, and the other subdiagonals correspond to the subdiagonals here, with the closest subdiagonal to the main diagonal corresponding to the one with the smallest delta omega, and the outermost subdiagonal corresponding to the one with the largest value of delta omega. We can see here that the density matrix looks rather circular, but we do not reconstruct the complete density matrix. The problem is that we are dealing with continuous variable quantum state tomography, and it is impossible to reconstruct the complete density matrix using an infinite number of measurements. In this case, we need to use an alternative trick to reconstruct the density matrix. Here, what we do is that we use a Bayesian estimation algorithm that, given the data that was measured, given a certain spectral response from the spectrometer, tries to reconstruct what is the most likely density matrix underlying this set of measurements. In this case, we see that the Bayesian estimation algorithm reconstructs a rather circular density matrix in good agreement with the initial measurement. We can then perform the same measurements in a different gas, for example, argon. Here we see again a set of different measurements in argon, where the topmost measurement corresponds to the situation where we have only one spectral component, and then we increase the spectral separation between the two spectral components. By taking the Fourier transform and extracting the corresponding amplitudes, we obtain this density matrix that is partially reconstructed. We can see already at first sight that it looks rather different from the one that was measured in helium. Now again, using the Bayesian estimation algorithm and the corresponding response function of the spectrometer, we now obtain this density matrix. So here is a comparison of the two measurements in helium and argon. We can see that both the raw data and the complete reconstructed density matrix look rather different between the two atomic gases. We can quantify this by measuring the purity, which is given by the trace of the square of the density matrix. In helium, we obtain a purity that is very close to 1, indicating that the photoelectron can be described correctly with a wave function. In argon, we obtain a much lower purity, indicating that the wave function formalism would not be able to describe correctly the photoelectron. So what is the difference between the two atoms? In argon, when we ionize, we end up with a hole in the 3p shell that has a spin of 1/2 and an angular momentum of 1, giving rise to spin-orbit splitting. We thus have two ionization thresholds that give rise to two different photoelectron wave packets that have different energies. The total ion photoelectron wave function thus takes this form, where phi is the wave function of the ion and psi is the corresponding wave function of the electron. We can see here that the ion and the photoelectron are entangled, such that when we take the trace over the ionic degrees of freedom, we will end up with a statistical mixture of electron wave packets, which is why we end up with a purity that is lower than 1. For more information about this topic, you can read these two papers, which are about an alternative method known as mixed frog to measure the photoelectron density matrix, or these two papers, which are the ones that I presented in this video.